Hello everyone, this is Computing from Scratch and welcome to our course on digital logic. Today we'll start a lecture on Boolean algebra. In the last class we discussed NAND and NOR gates, and in the class before we discussed the other digital logic gates and OR, XOR and XNOR. Today we'll dive into Boolean algebra and some of the algebraic operations that is possible with AND, OR and NOT gates. We'll not talk about XOR, XNOR, NOR and NAND just yet. Okay, so what does OR stands for? OR stands for options. And what does AND stand for? AND stands for compulsions. So, example, there is a point A. This is the starting point. This is your house. Okay. End point is your office. End point is your office, that is point B. Okay. So, you are going from A to B. There are different paths that will lead you to the destination. Okay, so there is a path named X, a path named Y and a path named Z that go from your house to your office. Okay, so all these paths are optional. Now when I say about X, Y and Z, they are not explicitly the paths, but these are variables that will say the state of the paths. X, Y and Z are variables that reflect the state of the path. Okay. Now what state am I talking about? I am talking about whether the path is free or blocked. There are only two states possible. 0 stands for the path is blocked. And 1 stands for the path is free. Okay, so X, Y and Z are variables. 0 stands for blocked path and they reflect the state of the variables, state of the path. 0 stands for blocked path and 1 stands for free path. So X can take any value. If X takes 0 value, that means there is a blockage. Like there is a blockage in the path and you cannot go. 1 stands for free, that means you can go, right? There is no blockage and you are allowed to go. So the states of X, Y and Z are not known beforehand unless mentioned. Okay, the states of X, Y and Z are not known beforehand. So they can be blocked or they can be free. Similarly, we can talk about the AND gate as compulsions. So your home is here, right? This is your home at the location A. You want to go to your office, which is at the location B. Okay, so when you want to go to your office, the path is like this. So there is a X path which leads to this point, and following which there is a Y path which takes you from this point to this point, following which there is a z path which takes you from this point to B. Okay, so x, y and z are the three paths. These are compulsions because you have to take the path x followed by y followed by z. Okay, now and is compulsions, but there is no order in there. Okay, so it is a bit, all these three paths have to be taken, but there is no order in there. Okay, so this path can be called as z, this path can be called as x, this path can be called as y, or any of these paths can be called as any one of x, y and z. Okay, so there is not a strict ordering to these paths. Okay, so but you have to take all the three paths to reach B. So their names keep changing, right? So now here also x, y and z are with variables which represent the state of the path. X means the path means x, y and z, these are the variables that represent the state of the path, like here 0 stands for the path is blocked and 1 stands for the path is free. Now these variables x, y and z can take any value, either 0 or 1, can take only Boolean value, can only take 0 or 1. So the path is either free or it is blocked. So how they represent the AND gate? Suppose all the paths are free, then you can go from A to B. Suppose y is blocked, that is value is 0, you cannot go anymore, right? Here also this represents the OR gate. From A to B, if all the values are 0, means all the paths are blocked, then you cannot go from A to B. But if one of the paths are free, then the value is 1 and you can go from A to B. Clear so far? I think it should be clear. So next we'll explore something different. We'll explore some of the Boolean properties. Okay, we'll explore some of the Boolean algebra properties. Okay, so there is a path x from A to B. Okay, there is a path x from A to B, and there is a path 0 from A to B. Okay, 0 means it is blocked, right? So whether you can go from A to B will not depend on the 0, it will only depend on the state of x, the value of x. If x is a 1, then you can go. If x is a 0, you cannot go. So here this means x or 0 is equal to x. This is identity law or the identity property of Boolean algebra. Okay, so let me erase this part also. So here you have two paths, okay, x and y, no, x and 1. To reach to this point the path is x, and then there is a free path, value is 1. Now you want to go from A to B, you only need to know the state of x or the value of x. If x is blocked, you cannot go. If x is free, then you can go. If x is 1, then there is a path you can go. That means that x and 1 is equal to x. Okay, and since I said the ordering does not matter, so if 1 came before and x came after, okay, if 1 came before and x came after, what will happen? The path up to this point is free, and then again it depends on x. If x is 1, then you can go. If x is 0, the path is blocked, you cannot go. So this is equivalent to 1 dot x. Okay, so x dot 1 is equal to x is equal to 1 dot x. Similarly here also, if we change the ordering, does it matter? If the left side path is blocked and the right side is x, does it matter? It is the same thing. It depends only on x. If x is blocked, you cannot go. If x is free, you can go. If x is 1, you can go. If x is 0, you cannot go. So this is equal to 0 or x. Okay, x or 0 is equal to x is equal to 0 or x. X dot 1 is equal to x is equal to 1 dot x. Okay, so this second part will be discussed in another property called commutative property of Boolean algebra. For now you just need to know that x or 0 is equal to x and x dot 1 is equal to x, which is the identity law. This is called the identity law of Boolean algebra.